So what I will try to do now is just scale up what Philippe has just been showing. So I will be building up on their data to try to link to large-scale mantle flow. And for doing that, I will try to use seismic anisotropy. So most of the data I will be used is the same kind of modeling Philippe just showed us that has been done by Sasha Goryaeva that is defending her PhD next Tuesday, sorry. And I have worked quite a lot with Dave for building up, so getting textures and anisotropy from this kind of data they have done. So the main point of doing that for studying the mantle deformation is that we have lots of observations on how the rocks deform when we are close to the surface. They get less and less common as you go deep. Even in the middle to lower crust, you don't have that many outcrops. If you go to the lithospheric mantle, we have a few outcrops still at the surface. When you go to the convective mantle, we have nothing already. And even for the shallow part of the convective mantle, the only thing we get is a few inclusions in diamonds, and you cannot use that for studying deformation. So the main point is that the deep mantle is not far in distance from us, but it's still something that you can really not observe. So the idea is to try to use the same kind of technique we have been using for the upper mantle for a while to study the lower mantle. Is the idea that if you have flow, and if this flow takes place mainly by dislocation creep that we know that produces a strong orientation, preferred orientation of the crystals, and if you know the anisotropy of the crystal, we can have a large-scale seismic anisotropy that can be measured, and if you know how to go this way back, we can go from the seismic anisotropy to a flow pattern. So what we need to do if you wanted to use this approach for the deep mantle, first we need to have a very clear observation of seismic anisotropies. You will see that they exist, but they are not so easy to interpret as the shallow mantle ones. Then we need to know how the minerals deform. So this is a large part what Philippe has been just showing us, which are the deformation mechanisms that are applicable to the different mantle minerals. Then we need to go one scale up. We want to know how this deformation can produce does it produce or not a crystal preferred orientation, and how does it evolve as a function of strain. We need to know how the mineral's elastic properties. We have some data now, and then using the texture and this elastic properties for minerals, you can calculate which will be the seismic anisotropy and try to compare with the data. So I will try to go one point after the other. So starting by the seismic anisotropy observations. And these are very nice pictures I stole from Ed Garniero's site. He has a really beautiful library of pictures on seismic anisotropy. And something that is quite remarkable is that we have been observations for a while from seismic anisotropy in the deep mantle. The first ones come from the late 80s. And we have people in this room that have been really the ones of the first that have been working on this, and probably that can explain much better than me these observations. But mainly, the first observations came from analyzing the waveforms from the waves that were traveling in the deep mantle, and the observation that they got is that usually the SH, the horizontally polarized S waves, were faster than the SV ones. Then this paper is one of the first that tried to use the usual shear wave splitting techniques that you use for the shallow mantle for looking at the lowermost mantle, the D double prime. And essentially, the main conclusion is also that they had SH waves traveling faster than SV, and they could have a first quantification of the intensity of the anisotropy on this layer. Okay, so this is a summary Ed Garniero did in 2005 of the observations of this kind of shear wave anisotropy they had in the lower mantle, D double prime, and there are many more in recent times. And if you go to the poster section, there's some nice data from Angelo Pisconti on the Atlantic now here. You see that we have quite a lot of observations. Still, it's patchy. We are not covering the whole D double prime. Something that was also came after this map is that we started to have in some places, observations from more than one ray direction, so from cross-cutting paths. And what they saw when they started to do this kind of observation is that the anisotropy you are seeing with the different azimuths of propagation was not the same. And then they start to treat more and more this data. And what they propose when they back project the anisotropy they see at the surface to the deep mantle is that in some places it was really SV that was faster than SH, but in some places they had to propose that the fast axis of anisotropy was inclined relative to the horizontal or relative to the core mantle boundary. So there's data on this kind. There is also global data from anisotropic tomography. So here are the seismic velocities. Here is the radial anisotropy. And you see there's quite strong radial anisotropy with in many places you have SH that's faster than SV. And if you do an average 1D model, you have a clearly SH that's faster than SV. You have some regions where the red dots here, where SV is faster than SH. But they're in much smaller areas in the mantle. And the last type of observations that can be used to detect anisotropy in the lower mantle the lowermost mantle, is to use the D double prime reflections. So this kind of reflections, so essentially they are analyzing waves that reflect at the top of the D double prime. They were first used for getting information on the phase change. And this kind of study, for instance, could also was also very successfully compared to have a double crossing that could correspond to a double phase change from Bridgmanite to post-perovskite and back to Bridgmanite in cold regions, for instance, in the mantle. And you see that most of these observations are related to cold fast velocity, so probably cold areas in the deep mantle. There are a few ones that are in the large low velocity provinces that has been interpreted as could be melt layers in the mantle. But some of these reflections have some polarities, and Tina has worked very lengthy on that, so she probably can explain better than me this. But some have polarities that cannot be explained in a simple way by an isotropic Bridgmanite layer that is on the top of an isotropic post-perovskite layer. So for explaining the contrast in velocity you see by analyzing these reflections, you need to have something else than two isotropic phases. And one possible explanation is that you have anisotropy, so that you have velocity variations in one of the two layers that is related to the fact that the minerals are oriented and get faster or slower velocities than what you had with as an isotropic phase. So the conclusion of this first part is that we have clear observations of anisotropy. We have something that we can use to try to constrain the flow in the deep layers, in the D double prime layer. So let's go to the mineral. And so here I will be using the data, the kind of modeling Philippe just showed. So this is the motion of a 100 dislocation that is gliding on the 010 plane. So this has been the molecular modeling simulations. And from this kind of simulation, so what Sasha did is to embed the dislocation in a big cell, apply stress to this big cell, and see what happened. So at the beginning, you have just the elastic deformation, strain that increases linear with stress, and at one time, the dislocation starts to glide, like here. And the stress you apply when it starts to glide is exactly the limit of stress you need. So the critical resolved shear stress you need on this plane to get your dislocation moving. So this is an important information if I want to model the textures. So she did this kind of calculation for all possible slip systems, so all possible glide directions and glide planes inside the post-perovskite structure. And what she also found doing this kind of calculation is that you won't not only have a dislocation glide, but post-perovskite can also twin. It means that you can have a shear inside the structure that can produce a very different oriented crystal, but we still have a coherent structure on the boundaries between the two crystals. These are the values, the critical resolved shear stress she got for the different types of dislocations at 0K, and then she did, and okay, that's just what is important, how the twins are important when I want to study texture evolution is that they produce a very strong rotation of the crystal, so it has a very strong effect on the orientation. And what is also important is that it gives a little bit more degrees of freedom in the ways I can deform the crystal. And this will be important because more degrees of freedom I have, it's easier to deform. If I only had the glide systems, I could only accommodate shear parallel to the basal planes. Here I can accommodate normal deformations parallel to the main axis. So it can help quite a lot on the deformation of the crystals. And okay, and then we needed something that was not at 0K. 0K is not at the temperature at the D double prime conditions. So she did also the calculations by taking into account the temperature effect on the dislocation glide. And these are the values she got for temperatures that are consistent and pressures that are consistent for the double prime conditions. And what is important is that you have a very strong decrease on the critical resolved shear stress with increase of temperature, and meaning that in D double prime, post-perovskite is as weak as the ferropericlase. So you don't have this contrast. You have in the lower mantle between bridgemanite and ferropericlase, in the double prime layer, both minerals are weak, really weak. So we know how it deforms. So now let's go one scale up, see how a rock that's composed by these minerals can deform. For doing that, what I do is very simple calculations that come from metallurgy. We have an aggregate that is composed by a finite number of crystals, and we impose how each crystal deforms. I impose that each crystal deforms by dislocation glide, essentially, so that is shear on well-defined crystal planes and directions. That will depend on the stress that is projected on this shear plane, and that will be normalized by the resistance of the dislocations to flow in this shear plane. This normalization factor here comes from the small scale calculations. So I have the slip system strength. I impose an initial texture, so I start from something that is isotropic, random, and then I impose a mechanical solicitation. I can impose either a velocity gradient tensor or a stress, and I will get the response. So this kind of model allows to calculate the texture evolutions, but it also allows to calculate mechanical behavior. So it's a way of also for scaling up the mechanical behavior from the crystal scale calculations to a rock scale. And what was missing here is that once I have how each crystal deforms, I need to see how they interact to give the aggregate mechanical behavior. And in this kind of model, we use a quite simple averaging way. What we impose is that the average of the crystal strain rates is equal to the macroscopic strain rate, and the average of the crystal stresses is equal to the macroscopic stress, and we do an iterative procedure where you're minimizing the difference on both strain rates and stresses to get the mechanical behavior of the aggregate. So you see the main input parameter on this kind of modeling is how hard are the different slip systems. And this is what I used. I did the models for an aggregate that's composed of 70% of post-perovskite and 30% of magnesium-wustite. And for magnesium-wustite, I also used the results from the atomic scale modeling from the Lille group. And if I do that, I can get a texture evolution. Textures are usually represented as pole figures, you see here. So what we are representing here is the orientation of the different crystal axes relative to the imposed deformation, to the imposed shear deformation in this case. So this is just a key for those that are not familiar on how to interpret these graphs here. So there are contours, density contours, and it means that at the beginning I have a weak, very weak preferred orientation. It's not completely random, but it's very weak. If I start to deform, I very quickly, at a shear strain of 1, I start to get a very clear texture. And if I continue to deform, the texture evolves. And it tends to stabilize at high shear strains. So a shear strain of 10 is a displacement of 10 times the thickness of the shear zone, so it starts to be a very strong deformation. And what we see is that we have a progressive reorientation with the 100 axis that tends to orient parallel to the shear direction, and the 010 axis that tends to orient normal to the shear plane. And twinning, it disperses a little bit this orientation, is what produces the secondary maximum here. That since you have a rotation around this axis, it disperses these two axes here. Okay, this is just one example. You can run thousands of models by testing the parameters. And I will choose just a few examples of the parametric testing. First testing is which is the effect of twinning on the texture evolution. So here is the model I just showed you with the twinning. And this is the same model without twinning for two different finite strains, so a shear strain of 2 and a shear strain of 10. And you see that the main effect of the twinning is that it slows down the texture evolution, because I have more degrees of freedom to deform the crystals, so I don't have to rotate them that much. And it allows a faster reorientation of the texture. I get my texture, my main crystallographic axes that are really parallel to the macroscopic deformation, while here I still have a small angle. I'm rotating slower. There are also some assumptions we do in the model, some simplifications. So one of the simplifications is we don't know precisely which is the stress exponent. So I tried 2 different stress exponents. We also do a linearization of the mechanical behavior inside the program. So there are different ways of doing this linearization. So these are just models with different approximations. And you see that, okay, there are some variations, but they are second order. Mainly the texture predictions are quite robust. The parameter that produces stronger variations is if I consider or not the twinning. All the more technical part in the modeling does not change a lot the predictions. So once I do that, I can also compare how my aggregate that's composed by 2 phases compare with the same deformation for a single phase aggregate. And you see that the dominant phase is post-perovskite, and it's really dominating the way the aggregate deforms. And there's not a big difference between the single phase aggregate and the 2 phase aggregates. The textures are a little bit weaker because I'm distributing the deformation over the 2 phases. So now let's test if the predictions are fine by comparing with the few experimental data that exist. And for that, instead of simulating a deformation by simple shear, I simulate a deformation by axial compression, because this is the type of deformation you get when you are doing diamond anvil cells, which are the experiments that have been done on post-perovskite. And this is the pole figures as before. This is the same crystal preferred orientation, but represented as an inverse pole figure. So what we are representing here is how the compression axis is oriented relative to the crystallographic axis. It's a little bit harder to read, but they have the 2 to give a hint, because these are how the results were often presented on these papers. And if you just compare the figures, it's clear that we are in complete disagreement. We are not reproducing what they get on the diamond anvil cell experiments. There are some complications on these experiments. The first one is that they have quite a lot of texture inheritance at the phase transformation. When they start experiments, they don't start experiments with post-perovskite. They start experiments with either perovskite or enstatite, and they compress it before the phase transformation. So they get a texture in the precursor phase that just gives an inheritance afterwards. But okay, so this can explain part of it, but it does not explain everything, because there is some evolution in the texture after the deformation. So we still don't know very well how to explain. Another possible explanation is that the stresses in experiments are very high. They are in the order of many gigapascals, much higher than the stresses we expect in the mantle. And here, the whole modeling is done in an approximation that is low strain rates, rather low stresses. So maybe if there is a strong stress effect on which are the active glide systems, we know that for olivine that it can be true, maybe that can be an explanation, but we still don't have a complete answer for that. If you try to compare with data on analogs, so other composites that have a post-perovskite structure, so calcium iridium oxide, that has the post-perovskite structure at ambient conditions, so we can do the experiments in a usual way. We do the experiments in the lab with bigger samples and lower pressures and lower stresses. Then you have a very nice correlation between the textures you predict, and these are shear experiments, and the textures we predict in the model and the ones they observe in the... So it does not work with the real magnesium silica post-perovskite, but it really has the same kind of structure with other post-perovskites. So this is what we can say up to now. So there's still an open question here. So let's assume that my texture predictions are fine, and then go one step further and calculate which will be the seismic anisotropy. So for that, I have to know which are the elastic properties of both post-perovskite and magnesiovustite. And what we'll do is, if I know this, I can calculate the properties of the rock by a simple averaging of the properties of the different crystals that compose the rock by doing the appropriate rotations to put all of them in the same plane. So these are the properties for the single crystals, and this comes from very recent data for post-perovskite, for atomic scale modeling, and where they also studied the effect of composition. Here I used a very standard composition and conditions that are okay for the uppermost part of the cold Debo prime, where you have more chances to have post-perovskite. This is the magnesiovustite ones. And this is the seismic properties we get for the magnesiovustite post-perovskite aggregate at these conditions. So what you see is that for the P waves, so here what is represented is P wave velocities as a function of the rock deformation frame. So you have fast P wave velocities parallel to the shear direction and slow P wave velocities normal to the shear plane. The shear wave splitting pattern is much more complicated. We have, even if you look along the shear plane, you have regions with very low splitting, regions with high splitting, lower splitting, high splitting, so we have a periodicity in the data. And what you see is that most of this area and most of this diagram, the bars are parallel to the shear plane, means that if my shear plane is horizontal, I will have SH faster than SV. That's what this plot is. And this is if you plot the two S velocities independent, or if you plot VP over VS ratios, so that you can compare with other kind of data. So just quickly, let's try to compare with seismic data. And the first question you have to know now is how should I orient my textures in a big mantle flow? So this is just one example of flow calculations for flow in the deep mantle. And what we get is that we can have very complex patterns. Here you have a nice folding of a slab that's plunging. But if you look, these are strain markers. The highest strains usually mark a stretching that's parallel to the core mantle boundary. So for a very first approximation to get the comparisons now, I would just show what will happen if you have horizontal shear parallel to the core mantle boundary. So this is going back to the shear wave splitting diagram here. And what I told you before, most of the bars are subparallel to my shear plane that is here, that I decided that it's parallel to the core mantle boundary. So in this case, I will have mainly SH that are faster than SV. If I try to look at the splitting data, then it gets a little bit more complicated. The SCS phases that are used for splitting, they are traveling more or less parallel to the core mantle boundary. So means that if I say that my shear plane is parallel to the fundamental boundary. They are traveling more or less parallel to my shear plane here. So they only see this part. From the whole diagram, the SCS waves are only seeing this part of the diagram here. All the rest, you don't have seismic waves to sample it. And you see that you have, first thing you see is that you have a very strong variation on the intensity of the anisotropy with a periodicity of 90 degrees, from very low anisotropy, strong anisotropy, low, strong, low, strong. What we also see is that if you look in the strong anisotropy regions, the fast polarized shear wave is polarized parallel to the core mantle boundary. So SH is faster than SV. You can have SV faster than SH, but in regions where you should see very low anisotropy in this kind of place. So I can explain fine where you see this in the splitting, but with this kind of diagram, I cannot explain the inclined fast polarizations they see in some regions. The only way to get with this kind of deformation, the inclined fast polarization, is to turn my diagram, means to turn my shear direction, so having a dipping flow plane, okay? If not, it does not work, at least for this model, this specific model I'm presenting here. And then, just a quick look at the D double prime reflections. In this case, the waves we are using have a very limited incidence angle also, mainly around 60 to 70 degrees. And so what I have to do is to compare what is above and below for this incidence angle. For this, I have to make an assumption on how the upper layer, how are the textures in the upper layer, how are the seismic properties in the upper layer. So what the hypothesis I did in the model I'm showing here is that bridgemanite develops no texture because it's deforming by dislocation climb, okay? That's following what Philippe just told. And then we just try to calculate with the energy of the reflected waves as a function of the energy of the incident P wave by varying both the incidence angle and the azimuth. And I will just show quickly what we have for the, so what we want to have to look here is the light blue curve here that shows the energy of the reflected P wave. And you see that here also you have lots of variation with some azimuths of propagation where you should see a positive contrast, and others where you should see that should be negative, but where the signal should be so low that you could not see, probably won't see anything on a seismogram. And I stop here. The idea is that we can use seismic anisotropy data to interpret the upper mantle. The problem we still have here is that in contrast to the upper mantle, we still have too many degrees of freedom. We still have many possibilities. Even if you say that we know how post-perovskite deforms, we still have loads of degrees of freedom on how the flow directions are in the deep mantle. So we need more seismic observations for sure, so that you can constrain better what we are doing with the models. And for the simplest models I showed you, we can explain most of observation, but not all of them. So we need to change the model somehow to explain at least the inclined fast anisotropy axis that you see with the SCS splitting.